Griffin's occasional series of Matlab tutorials on YouTube, and today we're doing linear regression and polynomial regression in YouTube. So Matlab comes with some sample data files, and car small is one of them. So you can see here that Matlab compiled 100 data points, and you got acceleration, cylinders, displacement, etc., and MPG. So one would think that the miles per gallon is dependent on, well, I suppose you could argue all four here, but we're just going to take displacement, engine size, cc's if you're an American, okay, litres if you're a European. So there's 100 data points, and if we just look at now, if you use the polyfit command, it won't work in this case. Why? Because some of the data points are not a number, NaN. So if you use polyfit, it's going to object. So we go to curve fitting, and there we are, and we just do a new fit. And we're going to call this poly 1. So a polynomial of degree 1 is a straight line. So displacement is the thing that causes the effect, and the thing that is being affected is MPG. I'm going to leave off center and scale for the moment, and you see here NaN, so it ignores the not a number. So I think there was 5 or 6 of them, so it'll plot for the 94. Gives you the little graph there, and it gives you the line of best fit here. So y, the f of x, so MPG is P1 minus 0.05874 times x, the displacement, plus P2, and P2 is 35.52. And if you go back to there, if you went back, you see that's roughly, say, guessing around 50 or 60. If you went back, it would hit the y-axis at 35.52. Okay, just let's look at the residuals here. And if you are doing more advanced statistics, the residuals should have no pattern. They should be randomly distributed, etc., etc. Just a slight bit of worry here that around the displacement here in cubic inches, that they all seem fairly negative. So, but just visually, they should be completely random. Okay, so we've done that. Just so the R squared value, how well do these points fit the line? The R squared is 64.54. So 64.54% of the y value, which is the MPG, is explained by the displacement. So let's see if we fitted an x squared component. So fit, new fit, and poly 2. X data is displacement, y data is MPG, degree 2. Again, it ignores the not a numbers, excuse the slight hoarseness in the voice. So y, the f of x, MPG is, I think, 3.1621 times the displacement plus P2, squared, displacement squared, minus 0.1375 times the displacement plus P3, 42.86. So if you extend that back, it'll hit there 42.86. The R squared is 68.79. If you see the two of them down there, there's very little difference. The adjusted R squared, the more terms you have, the you should get a better R squared, but sometimes you can overfit. So to compensate for the number of terms that you use adjusted R squared, and okay, it's gone up a little bit. So at the moment, we'd say of the two of them, we'd go with poly 2, the polynomial of degree 2. We'll do one more fit. And we're going to call this poly 3, a polynomial of degree 3. That's displacement. That is MPG. The degree is 3. So the slope of the x cubed is 8.9 by 10 to the minus 8, very small. The slope of the x squared is 9.8 by 10 to the minus 5. That is 0.128, and where it hits the y-axis is 41.76. Gives the r squared and the r squared adjusted. And as of the three of them here, you would take the one with the highest adjusted r squared, that's the polynomial of degree 2, that's 68.11. Hope that helps a little. Just one thing I suppose just before I go, if we look at the residuals, they'll come up now in a second. So there's the residuals for degree 3. There we are, and now if we look at the residuals for degree 2, coming up now in a second, and we've got the same slight worry here that around in the cubic inches here, a lot of them are quite negative and there's very few positives, so that would be a slight worry. Okay, so hope that helps a little. Thanks very much for listening.